Hey everybody, I was just kind of brushing up on the book and getting ready for your video where we're going to talk about how temperature can affect the rate of a reaction. And looky what I found in my book, an inchworm. Yeah, let's see if he can, do something for us. Dance for us, inchworm. Actually, I like to think of him as a 2.54 centimeter worm because we're all about the SI system here. Anyhow, this guy's going to go outside and let's talk about how temperature can affect the rate of a reaction and what is a catalyst next. Happy hump day! Well, hi everybody, hi. Mike here, and I kept him. I'm using him as a blatant prop now, the inchworm, and he's wondering what's going on, but it's okay. I would like to say that what if the little inchworm here was part of a chemical reaction and he had to, it sounds kind of terrible, but he had to collide with another molecule in order to become something different. Right now he's saying, these lights are so bright. Hey, welcome to show business there, Mr. Inchworm. But a good example would be this. This is an exothermic reaction just ready to happen, but it's not a straight path from reactants to products. There is a hump involved, what we call the activation energy. And so we've got where we start. Now he's in the way. You see, now I just got too cute with involving him, but now he's liking the attention, I think. And so what you already know about is the difference in energy between reactants and products is called the delta H. This would be an exothermic reaction. The reverse would be an endothermic reaction. And now what the inchworm is showing us is that you've got this sort of peak to get over. There's always, why doesn't this reaction just happen passively? That's because there's a hump of energy that needs to be gotten over, and we call that the activation energy, or EA equals activation energy. And it's measured the same way as is delta H. So, for example, it'd be in kilojoules per mole, or some amount of energy per amount of the substance that would react. And so it's not a direct path. So what happens here when we do this? How do I make this happen? I need to obviously not strike it. I want to start a movement. You activate it. Now watch out, inchworm, you're going to get hurt. What's going on right now? What's going on right now is that the molecules are just but if I give it enough energy, all at once, then you get sort of a chain reaction that happens. Why does that chain reaction happen? Oh geez, I better not put it on the paper. And not near Inchy, the inchworm. I got to make sure I keep in mind where he is. Let's, oh, now I knocked him over. Never mind. So why does that not happen, or not happen passively? But when I put enough energy into it, it did. And that is because once I got enough molecules over the hump, they can then use not just delta H, but the difference between the top of the activation energy. And by the way, if you take organic chemistry, they call this an activated complex. Basically means that the molecule has now acquired so much energy it can't do anything but become something else. And then it's a long downhill stretch. And where's that extra energy go from the top of the activation energy to the bottom where the products are? that energy goes to surrounding molecules, which help them get over the hump, and then they can get over the hump and give their energy to other molecules. Pretty soon, next thing you know, there's no more reactant molecules. And so that's how a exothermic reaction really works. An endothermic reaction still has a delta H to get over and an activation energy. And so if I was really, watch out, if I was to really quick just draw the same sort of graph for something that was endothermic, it'd be the same kind of graph except backwards. So what you would have is you'd have that the reactants would be lower in energy. You'd have to get over the hump still, but then to get to the products. And so here on the left would be the reactants. Here would be the products. This would be the activation energy. And this, my friends, is why temperature is the only thing that will change the rate constant. And so there is an equation that we're going to talk about next. It's called the Arrhenius equation. By the way, just to be thorough, this would be the delta H. No, Mike, sorry, I was thinking last diagram. This would be the delta H. It would be positive in this case. And so you'd have a higher activation energy for something that's endothermic than we would for something that's exothermic. Now, we're not going to really crank out a lot of numbers today. I'll let you do that in your homework. But I want to talk about how the temperature affects the rate of a reaction. And then it turns out that if you're driving through the highways of West Virginia, what's the easiest way to get from reactants to products is not to necessarily go over the top of the mountain, like this inchworm probably thinks, but to also, what if you could dig a tunnel? And that would make things much more simple in terms of energy, or much more easy to accomplish. So I want to talk to you about the Arrhenius equation and how temperature affects the rate of a reaction, and a little trick that we have up our sleeve called catalysts. Okay, folks, so before we get all mathematical about things, I want you to kind of visualize what's really happening when you increase the temperature of a reaction. Now, here's how a population of molecules behaves. So what you've got, let's say this is T1, and this is a temperature. So let's say that is at temperature 1. And you see the red line I've drawn. What happens is, as you have a population of molecules, only a certain number of molecules might have enough energy to actually react. And so anything that's past this particular threshold, that's a molecule that can get over the hump. Now, if you increase the temperature, here's what happens. That curve sort of spreads on out. And so let's say this is T2, where T2 is greater than T1. And what happens is you're going to have a greater reaction because more molecules can get over the hump. And this is expressed by something called the Arrhenius equation. So the Arrhenius equation, unfortunately, has a logarithm in it. But you've got this fudge factor here. This is called a collision factor. That's like saying basically it's a number between 0 and 1. And it's basically saying what's the probability that when two molecules hit each other that the reaction is going to happen. If it's 90%, that's a 0.9. So that's going to be a constant. Let's not really worry about that. Let's start thinking about what happens if I were to change this. This is the temperature in Kelvin. Of course, can't be negative. And so what happens there is, if it can't be negative, that guarantees that this particular term there, EA over RT, is always going to be negative. And that's an exponent. So we've got E, just think of E as 2.71. So let's go talk about what would happen if I were to change the temperature. So this would be temp change. And then we're going to see how that, oh boy, I really glossed over something there. And even Inchy was kind of concerned. He was like, hey, Mike, you forgot to say what K is. K is the rate constant. And so you know that the bigger K is, the faster the reaction goes. And if it's first order, then the bigger K is, the shorter the half-life, all that kind of thing. So let's talk about effect on K. Yep, see, okay, I know, that's what we're talking about next. So let's say I increase the temperature. What would that do? You got to think hard here. That would make temperature would become bigger. That would make this term smaller, but because it's negative, it would be smaller and negative. And so that would make K increase. And so if you can understand that, what if I decrease the temperature? Boy, I'm really trying hard not to write on him. A decrease in the temperature would then make this term this smaller, making this term larger and negative. That would decrease. And as you know, if K changes, that changes the rate. But you'll notice concentration ain't in here at all. There ain't no concentration in the Arrhenius equation. It specifically has to do with only the activation energy, which is coming up next, and temperature. So what if you did something like increase, decrease concentration? That might change the rate, but it would not have any effect on the rate constant, because you know we had all these kinds of rate equals K times concentration of A to some power. That is not part of the Arrhenius equation. And notice that the concentration is split out from the K. So this is directly affecting the K is EA and RT. And so next what we're going to talk about is, okay, so we already knew that in our minds, that increasing the temperature would increase the rate, and therefore the rate constant, because it would make it go faster as you get more molecules over the hump. What's this business about the activation energy of a reaction? How can we change that? We can do that using something called a catalyst, which we'll talk about just next. Okay, folks, let me talk to you about what a catalyst does. What a catalyst does is in about a gazillion different kinds of ways that would require us to just talk for eons about this. And if you go into biological systems, there's ones that are catalysts in your body that allow you to basically carry out combustion, but you're doing it at 37 degrees Celsius. You're not doing it at the temperature of combustion. Of course, you're doing it in little baby steps too. But a catalyst somehow, by either orienting molecules better or by somehow giving them a place where they can get or give electrons easier or whatever, it will lower this activation energy. So here's EA before, here's EA after. And so a catalyst, very generic term, is a substance which, as you could see, if you were riding your bicycle over that hill and you could go through this tunnel, you would get from R to P much quicker. A substance which increases the rate of a reaction by lowering by lowering EA. And by the way, it is not consumed by it, so you can't say, well, I added more concentration. That's something that would increase the rate of reaction. No, that's quite a different thing. And so let's see what happens. Okay, you're going to take a break over here, buddy. He's going to go outside when it stops raining. I don't know why I think an inchworm can't handle rain, but I just want, I've already kind of exploited him enough because I've got to juice this stuff up with a little entertainment, and he just saved my day because all I got next is a piece of potato. But if you were to go and, this of course is not temperature change, these are separate things. What if I added a catalyst? Add catalyst. What's that do to the rate constant? Well, adding a catalyst is going to make this EA smaller, which makes this whole term smaller, but it's negative. That will increase the rate constant. So you might notice when you read these verbose homework problems, they usually say, well, the rate constant of this reaction is blank at blank degrees. And so they always give you a temperature because it changes with temperature. And so perhaps, like in lab or whatnot, you might do a reaction at different temperatures, and you'll find out that it varies the rate and rate constant as a function that's kind of like a curve because of the fact that an E is in there, and therefore a natural log. And so next I'll show you something you can do along with me at home that will be an example of a catalyst. Okay, I lost him. I don't know. I went to go get some stuff and I lost him. Okay, hold on. Okay, all right, I found him. He's right here. There he is. I found him. Okay, he's just chilling out. Let's let him sit there. Okay, so what I was saying is before I let you go, if you want to do this really quick experiment in your house, you can do it alongside your kids. You just need some hydrogen peroxide and you know, some sort of container, you know, like this is a dessert bowl, and don't judge my hard water. Now, if you got some chicken livers, liver is just chock full of enzymes, which are catalysts that contain anything that oxidize something like hydrogen peroxide. If you oxidize it, you will find that you will make oxygen. And if you go ahead, and I took a slice of potato, and you know, you want more surface area than that, you know, so I took a shaving of a potato. Potato has enzyme in it called catalase, and we'll take a look at that one that I just popped in there, and you will see bubbles starting to form all over the place. And that's because, you know, I broke open some cells. They have an enzyme called catalase, which will convert H2O2 into water and oxygen. This happens when you put it on a wound, and so generally if we let that go for a good long time, which I'll do, I'll let it go for 5 minutes while I go put him outside, and we'll come back and see what that looks like later. But you can see already the amount of oxygen production we've got. Now, don't get me wrong, look at the surrounding hydrogen peroxide. If you leave that out for a day or something, it'll bubble, but it ain't going to bubble with the kind of vigor that it is near the pieces of potato. So, okay, buddy, it's time for you to go outside, and you're going to, hopefully it's done raining. So sign off with everybody. Inchy the centimeter worm says bye. And you folks, I'll say goodbye to you too, because I was going to come back later and show you it's bubbling, but I think it's doing a magnificent job. And so we'll catch you later. Bye.